For 50 years, the engine of human progress ran on a simple promise: computers would get twice as powerful every 2 years. That promise was called Moore's Law. It wasn't a law of physics, it was a threat. A threat delivered by one company to every one of its competitors. Keep up or die. That company was Intel, the undisputed emperor of Silicon Valley. For decades, its factories were the heart of the digital world, churning out the microprocessors that powered everything from supercomputers to the first personal computers. Its dominance was so absolute that its tick-tock development model, alternating between shrinking its transistors one year and redesigning their architecture the next, became the metronome for the entire tech industry. But then, the unthinkable happened. The company that wrote the law broke it. The empire faltered. For nearly a decade, Intel's legendary manufacturing engine seized up. Its factories fell behind, its rivals surged, and its crown was seized by a quiet, methodical giant from Taiwan, TSMC, the Taiwan Semiconductor Manufacturing Company. TSMC didn't design its own chips. It simply built them for others, and it did so with a discipline and reliability that Intel could no longer match. By 2023, TSMC's revenue had eclipsed Intel's, making it the world's largest semiconductor maker. Now, under a returning CEO, Intel is launching the most audacious, expensive, and high-risk counterattack in the history of technology. It is a multi-front war waged not just with silicon, but with business models and geopolitics, a trillion-dollar gamble to reclaim the throne. The question is no longer, can Intel come back? It's what happens to the global balance of power if it succeeds, and what happens to the world if it fails. To understand the scale of Intel's counterattack, one must first understand the depths of its collapse. It wasn't a single bad decision or a missed product cycle. It was a slow, grinding failure of execution that began around 2014, a period now known as Intel's lost decade. The crisis began with the 10-nanometer process node. Originally planned for 2015, the technology proved fiendishly difficult to manufacture at scale. The delays were catastrophic. What was meant to be a 2-year step became a 6-year marathon of missed deadlines and broken promises. Intel was stuck on its 14-nanometer process for so long that it became an industry punchline. This stumble shattered the company's tick-tock cadence of innovation, the very rhythm that had defined its leadership for a generation. As Intel's 10-nanometer process languished, its 7-nanometer follow-up was also pushed back, from 2021 to 2022, and then to 2023. The metronome had stopped. This created a massive power vacuum. While Intel was mired in its manufacturing crisis, its chief rival, TSMC, executed flawlessly. TSMC's pure-play Foundry model, building chips for fabless design companies like Apple, Nvidia, and AMD, allowed it to focus solely on manufacturing excellence. TSMC raced ahead, launching its 7-nanometer node in 2018 and its 5-nanometer node in 2020, seizing the undisputed manufacturing crown. By 2020, analysts estimated that Intel's 7-nanometer process was at least 4 years behind TSMC's equivalent technology. The empire wasn't just wounded, it was lapped. This wasn't just a loss of market share, it was a fundamental breakdown of Intel's core identity as the world's manufacturing leader. In February 2021, Intel's board made a dramatic move. They brought back Pat Gelsinger, a former Intel engineer and protégé of founder Andy Grove, to serve as CEO. Gelsinger's return was a signal. Intel was going back to war. Weeks into his tenure, Gelsinger unveiled a plan so aggressive it bordered on impossible. 5 nodes in 4 years. The roadmap was a brutal accelerated sprint through 5 generations of manufacturing technology: Intel 7, Intel 4, Intel 3, Intel 20A, and finally, Intel 18A. This was not a plan for catching up. It was a plan to leapfrog. The goal was to compress nearly a decade of technological progress into less than half the time, reclaiming process leadership from TSMC by 2025. The pace is unforgiving. Each node represents a new generation of technology that must be developed, debugged, and brought to high-volume manufacturing in under a year, a feat the industry has never seen before. It is a high-wire act with no safety net, betting the entire future of the company on its ability to execute at a speed it hasn't demonstrated in over a decade. To win, Intel cannot simply match TSMC's current technology. It must jump to the next generation. This is what Intel calls the Angstrom era, a new frontier in physics defined by two world-first innovations, both set to debut on the critical 18A process node. The first blade is RibbonFET, Intel's name for a new type of transistor. For the last decade, the industry has relied on the FinFET transistor, an architecture Intel itself pioneered in 2011. In a FinFET, the gate, the switch that controls the flow of electricity, wraps around the transistor's channel on three sides, like a hand gripping a fin. But as transistors shrink, this design starts to leak current, wasting power. The solution is the gate-all-around, or GAA, transistor. As the name implies, the gate now completely surrounds the channel, providing far more precise control and dramatically improving power efficiency. Intel's version, RibbonFET, uses stacks of tiny nanoribbons to create the channel, allowing for more performance in a smaller footprint. This new architecture is the future of the industry. TSMC and Samsung are also moving to GAA for their next-generation nodes, making it the new standard on the Angstrom-era battlefield. But it is the second blade that represents Intel's true secret weapon, PowerVia. This is a revolutionary change, not just to the transistor, but to the entire architecture of the chip. For 50 years, all chips have been built the same way. The power wires and the signal wires are all laid down on the front side of the silicon wafer, creating a tangled mess of interconnects. Imagine a skyscraper where the electrical wiring, the water pipes, and the elevator shafts all run through the same public hallways. That's a modern chip. It's congested, inefficient, and limits how fast everything can move. PowerVia is the architectural equivalent of moving all the plumbing and wiring to a dedicated service basement. It is a backside power delivery network, the first of its kind in the industry. All the power lines are moved to the back of the wafer, connected to the transistors above by microscopic vertical tunnels called through-silicon vias, TSVS. The result is transformative. By freeing up the front side for signal routing, PowerVia reduces voltage drop, improves signal integrity, and delivers a significant 5 to 10% boost to performance and density. This is Intel's ace in the hole. Its rivals are working on similar technology, but TSMC is not expected to introduce its version, called Super Power Rail, until its A16 node in 2026 or later. If Intel can make PowerVia work at scale on 18A, it could secure a genuine 12 to 18-month architectural advantage. Intel's final technological gambit is its biggest and most expensive. To draw the impossibly small circuits of the Angstrom era, chipmakers use a technology called extreme ultraviolet, or EUV, lithography. These machines, built by the Dutch company ASML, are the most complex instruments ever created by humanity. Now, ASML has built the next generation, the high-NA EUV system. The machine is the size of a double-decker bus, weighs 165 tons, and costs nearly $400 million per unit. Its new optics can print features up to 1.7 times smaller than previous EUV tools, simplifying complex manufacturing steps that used to require multiple exposures. Intel is the first company in the world to purchase and install one of these machines, a massive bet to secure its manufacturing leadership for the post-2 nanometer era. It's a gamble because the technology is completely unproven at scale, and the costs are astronomical. This strategy is a direct contrast to its rivals. TSMC, known for its caution, is deliberately delaying its adoption of high-NA. It plans to extend the life of its cheaper, proven low-NA EUV tools by using clever multi-patterning techniques. TSMC is letting Intel absorb the brutal cost and the steep learning curve of debugging the new technology. It's a classic strategic clash. Intel's high-risk, high-reward push for a technological knockout versus TSMC's methodical, cost-effective war of attrition. Intel's technological counterattack, therefore, reveals a fundamental divergence in strategy. The company's lost decade was a spectacular failure of execution on what should have been routine, evolutionary steps in manufacturing. Gelsinger's response is not merely to fix that evolutionary process, but to force a revolutionary one. This new strategy compounds multiple, unprecedented risks. There is the timeline risk of the 5 nodes in 4 years plan. There is the integration risk of debuting 2 brand new, unproven technologies, RibbonFET and PowerVia, on the same process node, 18A. And there is the adoption risk of being the first customer for ASML's next-generation high-end EUV machines. TSMC, having built an empire on decades of steady, de-risked execution, is deliberately avoiding this level of concurrent risk. It will adopt GAA transistors on its N2 node, but with a proven frontside power network. It will introduce backside power delivery later, on its more mature A16 node. It will let Intel bear the financial and technical burden of high NA before it makes its own move. The technology war is not just about who has the better technology on paper, it is about who has the superior strategy for managing risk. Forging a technological superweapon is only the first front in Intel's war. To truly challenge TSMC, Intel must also dismantle its own business model, a fortress that for 50 years was both its greatest strength and its most profound weakness. Historically, Intel operated as an integrated device manufacturer, or IDM. It designed its own chips and built them in its own factories, a closed, vertically integrated ecosystem. This tight coupling of design and manufacturing allowed for deep optimization and gave Intel a massive competitive advantage. But it also bred arrogance, complacency, and staggering inefficiency. Pat Gelsinger's new strategy, IDM 2.0, is designed to tear this fortress down. It rests on 3 pillars. First, revitalize Intel's internal manufacturing to regain technology leadership. Second, pragmatically use external foundries, including its arch-rival TSMC, when it makes business sense. And third, the most radical pillar of all, launch Intel Foundry Services, or IFS, and open its factory doors to build chips for the entire world, including its direct competitors. The greatest challenge for Intel Foundry is not technology, it is culture. For decades, Intel's identity was built on the unshakable belief that its own designs and its own factories were inseparable and inherently superior to all others. This manifested in a rigid, inwardly focused manufacturing doctrine known as copy exactly, where a process developed in one factory was replicated down to the last detail in every other, with no room for deviation or local optimization. This culture is the polar opposite of what has made TSMC a titan. TSMC's success is built on a legendary customer-first ethos, offering a level of flexibility, collaboration, and service that is the very bedrock of the fabless semiconductor industry. To compete, Intel must transform itself from a product company that dictates terms into a service company that caters to the demanding and diverse needs of its clients. To force this cultural revolution, Gelsinger has implemented a new internal foundry model. Intel's own product divisions, like its PC and data center groups, are now treated as arm's-length customers of the manufacturing division. They have their own profit and loss statements and must buy wafer capacity from Intel's factories at market rates. This radical restructuring is designed to impose market discipline, forcing a new culture of accountability, transparency, and cost consciousness that was sorely lacking during the lost decade. The ultimate goal of this transformation is Intel Foundry Services. The ambition is immense, to become the world's second-largest foundry by 2030. Intel is targeting an expected lifetime deal value of more than $15 billion with its external customers. The financial road ahead is perilous. The new Foundry unit reported a staggering operating loss of $7 billion in 2023. Intel expects those losses to peak in 2024 as it makes the massive capital investments required for its 5N4Y roadmap, with the hope of finally reaching break-even around 2027. It is a long, expensive, and uncertain path to profitability. To succeed, IFS desperately needed a major public vote of confidence from a marquee customer. It needed an anchor tenant to prove to the rest of the market that its technology roadmap was real and that its cultural transformation was underway. In early 2024, it got one. Microsoft announced a landmark deal to use Intel's 18A process to manufacture a future custom chip. The deal, with an estimated lifetime value of over $15 billion, was exactly the market validation IFS needed. Having one of the world's largest and most sophisticated chip designers commit to its most advanced, unproven technology node was a powerful signal. It told the industry that at least one major hyperscaler trusts Intel's roadmap and is willing to bet its own products on Intel's ability to execute. Intel's strategy to save its integrated model is, paradoxically, to break it apart. The creation of an internal foundry, designed to make the company more competitive, introduces a new and profound risk. To become a successful foundry for others, Intel must first learn to be a foundry for itself. The historical advantage of the IDM model was the tight, symbiotic relationship between design and manufacturing, allowing for co-optimization that a fabless company using an external foundry could never achieve. The new internal foundry model is designed to expose and eliminate the inefficiencies that this close relationship also concealed. But this creates a potential civil war inside the company. If Intel's own product groups, now operating with their own P&L, determine that TSMC offers a better combination of performance, price, and reliability, the new model forces them to consider using their company's chief rival. This is not a hypothetical scenario. Intel's design teams already outsource approximately 30% of their wafer production, much of it to TSMC. This dynamic could trigger a death spiral. External customers will be hesitant to trust IFS until it can prove its new nodes are stable and high-yielding with high-volume internal products. But if those internal product groups flee to TSMC for their most important chips, IFS will never get the production volume it needs to mature its processes, improve its yields, and lower its costs. Success depends on walking a razor's edge, making the foundry strong enough to win internal business on merit, while making it independent enough to win external business on trust. The final front in Intel's war is not fought in a laboratory or a boardroom, but in the halls of power in Washington, D.C. The escalating US-China chip war and growing anxiety over supply chain security have created the perfect political climate for Intel to leverage its most unique asset, its American identity. For years, the United States watched as advanced semiconductor manufacturing migrated to Asia. The COVID-19 pandemic exposed the profound vulnerability of this arrangement, leading to a bipartisan consensus in Washington that domestic chip production was a matter of national security. The result was the 2022 CHIPS and Science Act, a $52 billion program to reshore semiconductor manufacturing. For Intel, it was a geopolitical windfall. The company is the single largest beneficiary of the act, set to receive over $8.5 billion in direct grants, up to $11 billion in loans, and a 25% investment tax credit on its massive factory expansion projects. This government support creates a deliberately uneven playing field. While foreign rivals building new factories on US soil are also receiving subsidies, their packages are smaller. TSMC is slated to receive $6.6 billion for its Arizona plants, while Samsung will receive up to $6.4 billion for its expansion in Texas. Intel's larger package is a clear signal of its status as America's national champion in the race to reclaim semiconductor leadership. This government backing is the foundation of Intel's most powerful marketing message. In an era of friend-shoring and heightened concern over supply chain security, Intel Foundry is positioning itself as the secure, trusted, Western alternative to the Asian foundries that dominate the industry. This message is particularly potent for one customer above all others: the US Department of Defense. The Pentagon has long sought a secure onshore source for the cutting-edge chips that power its advanced weapons systems. Through a program called RAMPC, Rapid Assured Microelectronics Prototypes, Commercial, the DoD is partnering directly with Intel Foundry. The RAMP-C program gives the US defense industrial base, companies like Boeing and Northrop Grumman, access to Intel's most advanced process, 18A, for their sensitive military hardware. This effectively makes Intel the default, trusted foundry for America's national security needs, guaranteeing a baseline of demand for its new technology and de-risking the immense capital investment required to build it. Intel's geopolitical strategy provides it with a powerful moat, a protected business sustained by government subsidies and guaranteed defense contracts. This moat ensures the company's survival and provides a crucial financial safety net as it navigates its risky technological and business transformation. However, this moat does not necessarily help Intel win the broader commercial war. The vast majority of the global foundry market consists of commercial customers in sectors like smartphones, personal computing, and artificial intelligence. These customers, giants like Apple, Nvidia, and Qualcomm, are ruthlessly pragmatic. They prioritize raw performance, cost-effectiveness, and absolute reliability above all else, including the nationality of their supplier. TSMC's empire was not built on government mandates. It was built on decades of earning the unwavering trust of these commercial titans through flawless execution. While Intel's status as the trusted foundry secures a high-value niche, it does not automatically grant it access to the much larger and more lucrative commercial market. There is a significant risk that Intel could become a highly successful, but ultimately niche, national security foundry, while TSMC continues its reign over the commercial kingdom where the real prize, global market leadership, is decided.